से थोड़ा लो आवाज।
Myself, Priya Chaurasia, respected chief guest of the day, Sir UMESH KADHANE Sir, Dr. UMESH KADHANE Sir, President Seva Sadan Trust, Dr. Sanjay Dabrai Sir, Secretary Seva Sadan Trust, Shri Avinash Rajpal Sir, Sangeeta Madam, Head of Physics Department and Vice Principal, Head of Botany Department, Head of Microbiology Department, Head of Chemistry Department, Head of Zoology Department, and respected teachers from science and all other streams, my dear friends and non-teaching staff. On behalf of the Department of Physics, I welcome to all of you for today's mission, Space Exploration. Today's topic is space, endeavors and role of IIST. We begin with Saraswati Vandana. I request Professor UMESH Sir, Sanjay Dabrai Sir, Avinash Sir and all other teachers, please offer flowers and ignite holy lamp to Ma Saraswati.
We are the modern people, so we have got the electrical ignition. Saraswati Namastubhyam Varade Kamarupini Vidyarambam Karishyami Siddhir Bhavatu Me Sada. Saraswati Namastubhyam Varade Kamarupini Vidyarambam Karishyami Siddhir Bhavatu Me Sada. Saraswati Namastubhyam Varade Kamarupini Vidyarambam Karishyami Siddhir Bhavatu Me Sada. Saraswati Namastubhyam Varade Kamarupini Vidyarambam Karishyami Siddhir Bhavatu Me Sada. Thank you.
Thank you all. Now I request Sangeeta Madam to offer memento as a token of love to Professor UMESH KADHANE Sir. Now I request Lalwani Sir, please offer shawl and Shrifal to Dr. UMESH KADHANE Sir. Now I request Sanjay Lala sir to please offer memento as a token of love to Professor Umesh KADHANE sir. Now I request Vinita madam to please offer Tulsi plant as a sir, Professor sir. Sorry. Now I request Sangeeta madam to say few words.
I will request, before I start, I will request Lala sir to offer a token of love to our Sanjay Dabrai sir. Flowers. Plants. I will request Ajay sir to please offer flowers to sir. Sir का नाम क्या है? भरत पाटिल sir. उधर से नहीं उधर. Sir is the principal of Nehru High School, Vinod Patil sir. I will request, we have got the two beautiful guests with us. Omkar is our student also and brother of Professor Umesh. I will request Kashish madam to please offer a plant to Omkar sir. I will request Paramita madam to offer Tulsi plant to Bharat Dagre sir. Now last but not the least, our youngest guest of the day, Ashwin Kedane. I will request my TY student Ankita Jaiswal to come and offer the, he will be happy to, he is a future physicist. Thank you all, thank you so much. Now, as this our program is streaming across all the classes and across India, I think. So there's so much energy. So let us have all the positive energy together. I will start the Shanti mantra. Om. 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 Om Sahana Bhavatu Sahanau Bhunaktu Sahaviryam Karavavahai Tejasvinavadi Tamastu Mavit Vishavahai. Om Shanti Shanti Shanti. Please sit down. This mantra, please sit down. This mantra is a Shanti mantra. It is always a request from teachers and students to Parmeshwara. I will say Parmeshwara, Ishvara, not God. That please help us and protect us, because we are now in a journey of acquiring the knowledge. And during that, whatever obstacles are coming, please protect us from all this. The last three words, Shanti, 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 is all the hurdles or negativity came or occurred while arranging this program. It may be Adi Daivik, unseen, Adi Bhautik, seen, and then sometime when we have got ego that we are arranging this program. So whatever unknowingly has come while arranging this program, we request God that please remove all these dvesha from that and let all of us, all the students sitting in different rooms are at peace. Now I'll just say one shloka from chapter number 4, Adhyaya 4 from Bhagavad Gita. Shraddhavan labhate jnanam tatpada samyatendriyah jnanam labdva parashanti achirena digacchati. This shloka should not be said half, because this has got deep meaning. This has got meaning for different students. Student at the school level, college level, then when we cross 40, then we cross 50. So for today I am talking about the student studying in the college and schools. This says that means those who are dedicated and devoted, they only can get the knowledge. So if all the students sitting in G3, G2, 209, 216, 210 have little unpressed, you have to control your senses and bring it totally focused, what now Umesh sir is going to talk. So that is from my all, and sorry I couldn't, with all due respect to our Umesh sir, my favorite student, and Sanjay Dabrai sir, Vinod Patil sir, all the head of departments, and my teachers from junior college and degree colleges who have supported a lot, and our technical team. Now we'll start. I will request our Sanjay Dabrai sir to please enlighten us with few words, sir, please.
Thank you to Team RKT for organizing such a wonderful event. And all I would say, our students of tomorrow must take inspiration from Sir and be the tomorrow scientist. Thank you. God bless everybody.
Thank you, sir. Thank you so much. I'll request Lala sir to introduce our chief guest. Though words will be short to introduce him, so I will request Lala sir to have very short, because students are waiting eagerly to listen to Umesh sir. Sir, please. Lala sir.
Well, good morning, all of you. See, I think that introduction, even though it's so short from my side, it may be, I'm sorry for that. But whatever information or whatever introduction I'll give, this is all regarding our chief guest, Umesh KADHANE. Yes, Professor Umesh KADHANE is professor at the Department of Physics, Iist, Department of Space, Government of India, Thiruvananthapuram, Kerala. He is also a Deputy Director at High Thrust Propulsion System project, which is the part of ISRO. Professor Umesh KADHANE has a rich background of physics and space physics. He has completed his BSc in Physics at RKT College, Ulhasnagar 3. He has completed his MSc in Nuclear Physics, right? Sorry, I took that thing from UDP, Mumbai University. PhD in the field of ion molecule collisions from TIFR, Mumbai, followed by more than 3 years of experience with ion storage devices and mass spectrometry at the University of Aarhus, Denmark, and the University of Paris, Sudan, or say France. He has joined as an assistant professor in the Department of Physics at IIT Madras. Later on, after 2 years, he moved on to Indian Institute of Space, Science and Technology, Trivandrum, which is, he's a part over there also today, presently. After 10 years of so much work he has done, he has developed a lot of in-house projects like 3 mass spectroscopy and electron spectrometry systems. He is also guiding the students and the undergraduate as well as the postgraduate students, and has as well as PhD students, which is 12 in number. 4 completed, 8 going on. A part of his research is also related with space physics and substantially contributing to diagnostic systems, simulations, and overall system development of electric propulsion systems, EPS, at LPSC, Valiamala, ISRO. And this is all for the ISRO people, right? Presently, now is the Deputy Project Director for the High Thrust EPS for LPSC, a Principal Investigator for the 3 major payload activities at Iist, including the plasma measurement, instrumentation payload around the Earth, Mars, and the Venus. Iist has accomplished 2 space missions under his leadership in 2019 and 2023, and he has set up his also laboratories at his own place. And this is the internationally renowned Atomic Molecular Physics Laboratory at Iist. He is an avid educator with a keen interest in putting forward all his scientific ideas and the theories in front of our student community and the public. With all our curiosity, I always welcome Umesh sir to this dais and take over for the lecture. His lecture will start within a few seconds.
Thank you, sir. Thank you for such a lovely introduction. But I think it's very short. We are given the introduction. Now I think all the students are ready for journey to the moon. I am not able to hear from the voice from G2 and G3. I hope teachers have heard. So I will just listen afterwards. I'll just request our chief guest, Dr. Professor Umesh sir, to please start the talk. Thank you, sir. Thank you so much. We have to just hold this mic.
Sorry?
This is interactive. So you can remove the dice, you can directly come here.
Yeah, that's better. Yeah, that's better. That will be better, yes. Yeah. And also the presentation you will have.
Yeah, I can play. Immediately, can I connect?
Yeah.
Yes.
Okay. Now can you hear me? Is it possible? I hope online also people can hear me. It can be here, no problem. That's okay. We'll keep it here. It's good for me. Yeah. I have to move? No, how to change the slides? No. How will you be doing? Then can I get that here? I'll move it. Huh? No. I'll do it. No. This is okay. It's okay. Let's make it simple. If something I have to go back to, I know where what is kept. So, okay. So good morning to all, and I am quite sure anybody who is listening to me today have absolutely no idea or no scale of what is going on in my mind. When I was hearing Lala sir talking about me, it's you can't imagine. I still remember these people teaching us. Okay, they have left extremely strong impact. I still remember Sangeeta madam had just joined the college, so she was also new, and we also were just starting the course. So for us everything was new. So Sangeeta madam represented an enthusiasm. When Lala sir came and taught us, it represented pragmatism. He was like that time, and he is today also the same. When Deshpande sir used to troubleshoot the circuit, we learned from him objectivity. When Phadke sir used to teach us and Phadnis sir used to teach us. We used to learn not only physics from these people, we learned personality, we learned characters, and the impact of that is impossible to show here to you all. But all I can say is, I was just thinking today morning, what will I say? Okay, so there are two things I would like to say to you. So the first one is, I brought my my son today to show a very special place in this building. It's the first notice board near the chemistry lab. I took him there, and in January 1993 I was standing there, and Mala Bhonmik madam came out from the lab, and she said, Umesh, you saw that there is a notice in that notice board. I said, what is that? In Mithibai College there is a quiz competition which is arranged by BARC, and you have to go. Okay. Okay. So, sorry, my voice is very bad because I've been traveling too much. She said, you have to go. I said, madam, I have gone maximum up to Ambernath by myself. I cannot go to Bombay, and Bombay College, meaning those days, now at least you people are well connected via internet. Those days it was like out of the world for us. I won't go. She said, nothing doing, you have to go. I will talk to the principal, we will pay for your train ticket. Okay. So madam ne bola to chale jate hain. So me and my friend Shri we went. We thought जाएंगे वापस आ जाएंगे, एक दिन का जाने आने का पैसा मिलेगा. We went. I qualified in the written test. I was also selected as one of the teams, and our team got the first prize, and I got the special prize from a very senior scientist. And I still remember that day, because I was just telling madam also in the morning, it is very hard in person's life to identify one moment in life where you can change. This is the moment which my life changed. But I can tell for sure that there was one moment, that when I was walking down the steps to take my prize that day, that is the day I decided that no, I won't stop only doing my BSc or MSc. I will go ahead, and I can go ahead. And this was possible because that day I was standing near the notice board, and one of my teacher here was insistent that no, you have to go. And that has changed my life. Otherwise I wouldn't be here. As simple as that. Okay. The second thing I wanted to tell before I start talking about my present institution is that I'm sure a good number of you, or perhaps all of you, have heard this name, Harivansh Rai Bachchan. So he wrote a very nice poem. He used to write a lot of nice poems. So he wrote one which is very famous, called Madhushala. Have you heard of this? Madhushala? So if you go through that poem, you learn that, in life you have to find your own Madhushala, whichever way you find. Okay? And a teacher is a person. It doesn't have to be a college teacher or a school teacher or a parent. It can be anybody. A teacher has to help you find your Madhushala. This place helped me find mine. I hope it is still doing that job and making thousands of you find your own Madhushala. And I cannot express in words what I feel about this place. And when I see these people who made our personality, and when I say our, it's not just me, because I know several of my friends, they are equally influenced by you. So I am ever grateful. Thank you very much to you and to this institution to be what you are. And that is not easy. I have been to institutions in India, in Europe, in Japan, and I am also now I was part of an elite institution like IIT Madras, and now also I am part of a very big institution. I know how difficult your job is. And I am so proud of you, and I am so grateful to you that you are still doing that. So with this, about my home college, I would like to talk about my present place of work. It is called Indian Institute of Space Science and Technology. It's an institute which was started by Government of India under Department of Space to encourage young scientists to be created to join for Indian space program. So, actually, can I have the mouse, please? Yeah. This is our group website. You're most welcome to see the details of what research we do. Okay. So where is IIST? Indian Institute of Space Science and Technology is in the southern tip of India here in Trivandrum, or Trivandrum is a shorter version of the main name Thiruvananthapuram. It's a deemed to be university. It's a young institute. Compared to this college, it is really very young. It started in just 2007, and this is how the campus looks. And it is India's or Asia's first space university. And since we are under Department of Space, we are actually a sister organization to Indian Space Research Organization. And because of that, till recently, all our BTech students had a bond with ISRO, that once they complete their BTech degree, they will be offered job in ISRO. Now also the job is offered. Previously, the bond involved some money. Now money is not there. They still get a job offer. Another big advantage is, of course, we have a seamless interaction. We can always go to ISRO centers and so on. So we have 3 BTech streams: aerospace engineering, electrical and electronics, and engineering physics. We total approximately 150 students we admit every year. These students are taken from JEE Advanced, just like IITs. We have 15 master streams with 170 students per year, and more than 200 PhD students. Again, we do have a lot of international MOUs, and it's a fully residential campus, so all the students have to stay on campus, and we have accommodation for 1,000 students. Now I'm coming to our lab, the place, my contribution, I shouldn't say my contribution, but whatever, my work. So this is my work. My basic training is in atomic and molecular physics. So obviously my molecular physics is my strongest area. So I spent maximum time on that. For that we have developed a lot of laboratories. I will talk about this. Parallelly, ISRO was in need to help designing a very futuristic engine design, which is a plasma engine. I will talk about that also. So there we are helping ISRO to develop electric thrusters, plasma engines. We are also interested in building spaceborne sensors. We already have accomplished 2 missions. Our labs have built 2 instruments and launched already. And we are preparing a 3rd one, which will be launched by next January. And we are also part of the Venus team. We will be building an instrument which will go to Venus. We are also helping another ISRO center for a very futuristic navigation system based on cold atoms. But of course, this is a very large domain. And by the way, this is by no means complete. There are many other things, but I can't just put them here. These 3 are our 3 labs which we have established: Atomic and Molecular Physics Lab, Electric Propulsion Diagnostics Lab, and Sensors and Payloads Development Lab. But of course, life is too short. So I like to quote my teacher. One of my teacher is Mirza Ghalib. हजारों ख्वाहिशें ऐसी कि हर ख्वाहिश पे दम निकले, बहुत निकले मेरे अरमान लेकिन फिर भी कम निकले. There is much more to do in life. Okay, so I'll just quickly give you, I'm going to show you a lot of photographs because this is not the time that I will teach you physics or anything, and I cannot. Okay, so you will see a lot of photographs. Some of them will make sense to you, some of them won't make sense to you. That's all right. Okay, it's just the day 1. Okay, so this is our lab, Electric Propulsion Diagnostics Labs. We have built 3 labs within IIST. So this is one of them. So what you see over here is a plasma thruster built by ISRO. And when it is fired, it looks like this. And I don't know how many of you are aware of this, but you must have seen a rocket being launched. So normally, a launch of rocket involves a lot of fume and fire and so on. Those are chemical engines. They are very powerful, but they are not very efficient. Whereas these engines, they are not very powerful, but they are at least 10 times more efficient. So in space, if you want to launch 1 kilogram in Earth's orbit, it costs you about $20,000. So $20,000 is roughly 2 crore. No, 20,000 is how much? 2 lakh, 20 lakh rupees. Roughly 20 lakh rupees for 1 kilogram. Okay? And one communication satellite is typically 4,000 kilograms. Okay? And in that 4,000 kilogram satellite, which we use for communication, out of 4,000, more than 2,200 kilograms is fuel. More than 50% is fuel. Because the satellite goes in the orbit for 15 to 20 years, and every day you have to correct its orbit, and you need fuel for that. If you have an engine which is 10 times more efficient, you require 10 times less fuel. And that means you can make lighter satellites or more efficient satellites. So that's why this technology is very attractive, but difficult to master. And more importantly, nobody will sell you this technology. You have to develop yourself. So that's why at Iist we built a facility here to devise instruments which will help ISRO build this instrument. Because when this engine is fired, you have to test how that engine is performing so that we can correct it and build it better. We help ISRO doing that. For that we build their sensors, test them in this chamber, and then we supply to ISRO. So these are the kind of sensors we built. The test in this vacuum chamber. The electronics also is built by our students in the lab, and then we supply. We take it to ISRO facility. This is where the sensor is mounted. We are standing inside a vacuum chamber. I don't know how many of you know what is a vacuum chamber, because you can't do all these things in air. You need vacuum. So this is a vacuum chamber. Okay? These are two very bright students with me. Shri is now in US. She is actually instrumentation engineer. Gautami is now in Germany. She is a power electronics engineer. But now they are good at plasma physics, because our project requires plasma physics. So it's an interdisciplinary research. So they built the data acquisition and control, you can see here. And now we are moving to the next stage. This is a new facility which we have now at another ISRO facility. And this is where the new system is coming up. The design and conceptualization is done with our guidance, because we are designing the diagnostics. This actually a robotic system which is designed for this electric propulsion unit, and that is designed as per our design requirement. It's built by an industry in Pune, but it is by our design. Now, this was about the electric propulsion research. This is about the sensors and payloads. This is one of the sensor which we built and launched in 2019. This was launched in April 2019. This is a picture. This is a custom that one day before the launch, those who are involved in that mission, they go closest safe distance. Of course, this thing is powered already. It contains more than 160 tons of highly inflammable explosive material. So we stand about a kilometer away from it and take a photograph. So this is in 2019. This is this year, April. This is our payload, second payload, which we tested in our lab. We built this in our lab, tested it in our lab, and this is mounted on top of the rocket here at this point. Okay? And this was launched on 22nd April. This is again our pre-launch photograph. I believe you know this face already, because Chandrayaan now everybody knows these people. But the other guys with this special t-shirt, these are all our students and faculty members, myself, our registrar, our director. This is Dr. Suraj, he is from Aerospace Engineering Department. This is Dr. Sudarshan Karthik, he is from Avionics Department. And these are all students working with me. This is my senior most PhD student, and this is another student who was working with me. Now she has joined as a scientist in New Delhi. So this is our mission patch for the Aries. Now I'm just showing you photographs, okay? And I just told you that it costs a lot of money to launch things in space. Are we launching it for fun? Because the box which we launched here, the weight of this box is about 3 kilograms. That means we spent 60 lakh rupees of your money, because you are paying taxes, right, to launch it. It took us 5 lakh rupees to build it, right? So why did we do it? So I'll quickly tell you. There is something which I will tell you at the end which cannot be priced. But what I can price for you, that I will tell you now. We are talking about what happens when the sun becomes angry. Whenever the sun becomes angry, it throws material at us. That material comes and hits our atmosphere. Fortunately, we have magnetic field. So our magnetic field protects us. But because of that, we create something called an ionosphere. So about 300 kilometers onwards, we have a belt which is filled with ions and electrons. And ions and electrons is a very good conducting material, so it moves. And when they move, okay, I don't know how many of you are from physics, but whenever you have a charge is moving, you have a current, and that current is not constant current, it is moving, meaning it is changing current. Whenever current changes, magnetic field changes. Whenever magnetic field changes, it induces EMF. And that EMF is induced in anything which is conducting. And on ground, we have lots of things which conduct. Long distance electrical lines conduct, water pipelines conduct, and these then experience extremely high voltages, and it can cause permanent damage to infrastructure. Okay? And you know, sun goes through solar cycle, 11-year solar cycle, and now it is reaching the maximum, and very badly reaching maximum. So whenever sun is angry, we receive a very large flow of high energy particles, and they cause a lot of disturbances. Our payload is actually designed to measure this flux as the satellite is going in the orbit. So our second payload, which we launched in April, it is in now 600 kilometers orbit and continuously measuring and taking data. And it is continuously telling us how the sun is responding, or how we are responding to the flow of high energy radiation from sun. But what I want to show you here is what is going inside this. So these are the sensors. These are the two sensors. This is a cut view. I'll not describe you everything. This green thing is a circuit board. These are some mesh for some selection of ions. And this is the main electrical board, and then these are DC-DC converters. This is how the circuit actually looks. This is designed by our students under the guidance of 2 electronics faculty and 1 mechanical faculty. And you can see this is the sensor board, and this is the main control board. Okay. Then in our plasma chamber facility, we test these probes, how they work, whether they respond to the plasma correctly or not. And this is the only facility in the country today where we can simulate the plasma environment like the ionosphere and test the payload. And that is created at Iist. And then we have this thermal chamber. This is not in Iist, this is in VSSC. This is a vibration shaker. So we have to recreate all sorts of conditions this instrument will go through before we send it to space. After doing all the tests and calibrations, this is the test data. We send it to space and we get some data. I'm deliberately avoiding telling you what this is because then it will take time. Okay, so don't feel bad. Okay, so all I want to show you are some pictures of some data which came from our instrument. Whether it is useful, useless and all, we will worry about it separately. Okay, so this is one typical data which we get from a given orbit. This is the orbit in which the spacecraft was just above India, and we collected this data. And this is a special event where normally we should have got only one peak like this. We got multiple peaks, and this was a very special signal because this happens because, okay, let me put it this way. Imagine you have a glass ball, and on top of this glass ball you have put a rubber covering, or jelly. Above this glass ball you have put a jelly. Okay, and now somebody comes and punches that jelly, so there will be some vibration in the jelly, right? Same thing happened actually. On 21st April, sun was very angry. It shot a beam of coronal mass ejection towards us. It didn't actually shoot it towards us, it simply threw it in space. We were in the way. Our fault. It could have launched somewhere else also, and it does launch. So it so happened that we were on the way. So we received this punch after 3 days, and that punch caused this fluctuation. Okay, now if this fluctuation is what it can cause, this means the oil pipelines, the water pipelines would have carried hundreds of amperes of current because of the induced EMF, and that can cause fire, that can cause leakages due to electrolysis. So you have to take care of such problems. Okay, now people are intelligent, they know what to do. Okay, don't worry, it might sound very alarming, but it's not. Okay, again this is again some space data. I'll skip this for today. Okay, now so far what I was telling you was about what people do to go to space. Okay, you can say a good number of things have to be done by engineers, and of course they are the professionals, they have to do it. Okay, but not everything has to be done by engineers. When it comes to expert jobs, we hire engineers. Okay, but the day-to-day jobs we actually do with physics students. Okay, so now slowly I am going to shift to what physics students do. Okay, so the payload which you saw, which we launched, was possible because we could do a lot of tests on ground. You have to show your instrument is going to do what you claim it is going to do. Okay, and I can tell you one big secret of ISRO's success. Their review process is a torture. Review process is a torture, and I'll give you just one example. I went with these two boxes. I am the PI, I am the in charge of this project, so I took these boxes, went to the ISRO quality control center and said, we want to close this box. Now everything test is over, now we want to close the box. Okay, close the box. So this box goes on top of the other box like this. You see this? Like this. And you put these bolts here, all these corner, you see these? You put these bolts, box is closed. I started putting the bolts. They stopped me. They asked, how many times you had already bolted this together? I said, I don't know. We used to tighten it whenever we are doing the test, we will connect it, do the test. No. You should have counted how many times you put the bolts. Normally we don't care, right? Like you must have used the tap. Anybody asks how many times you have operated the tap? You don't. They ask, how many times did you put these bolts? And we had no answer. They stopped the whole process. A big meeting was conducted. All experts were called. They checked the bolts. They checked the threading. They gave clearance. This is called NCRB. NCRB is, I forgot, non-confirmation something board, review board. Meaning if something you have deviated from, some mistake you did for some reason, instead of putting 2 centimeter wire, you put 2.3 centimeter wire. So you are deviated from the design. They will not go ahead. It will go to some expert committee. They will sit and check why you did this, whether it is good enough, not good enough. So it took us a lot of time to pass every step. But that is why they are successful. Okay? And that too, every time we get some margin because we go with students. Okay? So whenever I say that this is built by our students, then they become little soft. But their own people, for the missions like Chandrayaan, some of our guys who are now working in ISRO, those who are working on the project, almost for a month they could not even go home. They will not let you relax till every test is passed. Okay, that is why they are so successful. So for us, it was a great achievement to pass their test, and not just pass their test, to reach the milestone and acquire this data. Okay, but how was that possible on ground first? So for that we have to build some test equipments on ground. Okay, so there are some pictures again I am going to show you. These are all done at Iist workshop, designed by physics students, MSc physics students, BTech engineering physics students, and this is a plasma source, home built plasma source. This is another plasma source. This is an ion source. All these are built by our students. These are 2 test facilities. This is one big chamber, vacuum chamber. This is another smaller chamber, because all these tests have to be done in vacuum. Our students have not built them, but they have designed it. Okay? And they have designed it up to the engineering drawing. MSc physics students have designed this up to the engineering drawing. The only thing they have not done is to cut the metal and weld it. Okay? So this is done at the institute. So any mission, when we design, we go through 3 questions. And I think it's not just about a mission, it is about life. There are 3 questions you should always ask. Why, what, and how. And in this sequence. If your answer to the first is very clear to you, you will find the answer for the second. And if the answer to the second is clear to you, you will find the third. Okay? So every mission, whether it is a space mission or mission for life, these 3 questions are very crucial. So we ask ourselves, why? Why do we want to do this? We have our reasons. One reason is, of course, to study the ionosphere. But that's not the only reason. In fact, that is not the primary reason. The primary reason is what will come at the end of this talk. The second is what to do. Okay? That is where the job of a teacher comes. Okay? We tell the students, okay, what is to be done. Then comes how to do it. Okay? Now that is the fun part. Many times we know how to do it, we don't tell the students. We just tell them, okay, this we have to do. You find how to do. And you won't believe, sometimes they come out with ideas which are far better than what I would have told them. Okay? And that works. Many times it doesn't work. Sometimes we definitely allow them to make something which we know is not going to work, because sometimes that is important. Okay? In life, sometimes failure is more important than success. Sometimes, not always. Okay? So we sometimes deliberately let them fail so that they understand how failure tests. Okay? We have a lot of failures, but because of that failures, I will show you the end result at the end of the talk. Okay? So this is all the way about what we do as sort of engineers, training people like engineering. Okay? But let me now come to what a physicist is doing in this business. Okay? Now suddenly I am changing the subject. No, it's the same subject. You will see at the end. Okay. So, from the days of modern science, people used to think that Earth is a very unique place, and there is no way you can have very easy situation where all chemicals can come precariously together and form an organic life what we know. But then in 1960s, 70s, slowly people thought, okay, maybe there are other possibilities, but making life requires organic molecules which are very large, lots of atoms working together. That's a bit hard. We thought, apart from Earth, the rest of the planets in our solar system, they are either rocks or they are gas giants like Saturn and Jupiter and things like that. But slowly we learnt more with the many space missions and astronomical observations. We learnt that organic molecules are not so difficult to find, because initially people thought only in like this kind of protected environment, ionosphere, magnetosphere, ozone layer, everything is required for life-like molecules to form. But that idea is now gone. Now we know that organic molecules for life, whatever we require, are already found long back on comets, other planets, not just planets, on other moons of other planets, on asteroids. They are already found. And one most recent example I would like to show here is this. What you see here is a small capsule. This was brought back by a space mission called Hayabusa 2. Inside this capsule was a sealed container. In that sealed container was a 4.5 gram sample of an asteroid Ryugu. So a spacecraft went there, Japanese spacecraft, picked a sample, put it in that bottle, put it inside this capsule, and then this capsule was brought back to Earth. Fantastic mission. They got only 5.4 grams of this sample of Ryugu. It landed in December 2020. They took 2 years to open the capsule, because you don't want to contaminate the sample. And if there is a possibility that it contains some very dangerous virus, you do not want to contaminate the Earth. So they did all sorts of precautions. Everything is handled remotely, and they opened. And then they did the analysis. What did they discover? 2 very shocking things. First, this sample came from an asteroid. This asteroid was formed before any planet was formed in our solar system. And the second shocking thing is, the small part of that asteroid contained more than 20 amino acids. You know what amino acids are used for? To make our body protein. That means a tiny asteroid which was formed before planets were formed contained amino acids. We thought we are special. We are not special, right? So then the question is, at what stage really the life starts? Okay. This is just one. The next sample is coming from another mission. It is called OSIRIS-REx mission by NASA, and the asteroid is Bennu. I strongly advise, if you haven't already seen the video, please have a look at the video. It's a fantastic exercise where they went to an asteroid. It's not a very easy thing to go to an asteroid, you know. Why? There is no gravity, almost zero gravity. So if you want to pick up a stone from an asteroid, in the process of picking up, you may get actually launched in the space. Seriously, it is not easy, because that object has such a small mass. There is no gravity. See, we take gravity for granted. Okay, if I give you something to dig in the ground, you will start digging, no problem. If you try to do that on moon, it is fun. Every time you hit the ground, you will be lifted up. Okay, because the gravity is much less. And if you try to do the same on a comet, then you will not get lifted up, you will actually escape from the comet. Okay, that is why spacewalk is very dangerous. Okay, if an astronaut by mistake or with anger bangs onto the spacecraft's outside, he will go. Okay, that is enough, because the gravity is weak. Okay, so you should see the video how they collected the sample. Okay, so this is the mass analysis of that sample and what all they got. So then coming back to the question, when exactly the organic seeds of life form? So normally what happens? You form a star, and the rest of the material around the star forms something called a protoplanetary disk. Something like this. So the stars sit in the middle, and a disk is formed. Okay? And in this disk then, lot of collection of material happens over a billion years. And then planets will start to form. Okay? It takes billions of years. Okay? And this is not a story. This actually happens. These are the actual pictures taken by telescopes, radio telescope. These are, in fact, all of them are taken by ALMA radio telescope. All these are stars which are in the process of forming their planets. You can see some of them already having some ring-like structures. These are actually in the process of forming planets. Okay, this is one example. Okay, so now this is how the processing is happening. The star is burning in the center. It is producing lot of reactions and also producing planets, asteroids, meteoroids. Okay, once the asteroid hits our Earth, it becomes a meteoroid, comets, and so on. So this material is very, very special. And this is where the origin of life is hiding. And we have to learn about it. So that is why we need to study this in space. We can't do that on ground. Is it my phone? Okay. So, what are places we have seen these organic molecules? So these are all we have seen on comets. These are actual measurements, okay, by space missions which have gone to these places and done the measurements. So these are on the comets, asteroids, meteoroids, dwarf planets like Ceres, Pluto, planets like Pluto, Saturn, Jupiter, Titan, Triton, Enceladus, and so on. So these are the places where we already know a lot of organic material exists. Okay. Now the question is to identify ways in which this organic material is formed. Again, I am not going to take too much time, so I will skip this part. Actually, this might be interesting. Now, So I'll just talk about only this example, not all. This is my favorite example. Titan is a moon of Saturn. It has atmosphere, 1.5 bar. Ours is 1 bar atmosphere, it is 1.5 bar. Only difference is ours is an atmosphere we can live. This atmosphere is highly poisonous. It's 96% nitrogen, few percent of methane, and then the rest is hydrogen cyanide, which is of course not very welcoming gas. Now this picture what you see here is the picture which is actually taken by the lander on Titan. And all this yellow material what you see is an organic polymer called toluene. It's not one polymer, it's a series, or it's basically a family of polymers. Okay? And this polymer is like a plastic sheet holding lots of different types of molecules on top of it. Okay? So this can actually act like a, what should I say, a molecular breeding ground. Right? Molecules can stick to it and then they can do reactions. And this is formed, and the beauty is that the whole moon is covered with this material. Pluto is covered with this material. Many comets are covered with this material. The question is how this material is formed. Okay? Then second is, will this material help forming the molecules of life? Okay? And how then this material is formed? The simple theory is that this is Saturn, okay? This is Titan. And what you see over here is the magnetosphere of Saturn. What Saturn's magnetic field does is the high energy radiation from the sun which is coming is the magnetic field, the charged particle radiation, okay? Sun doesn't only emit light, it emits lots and lots of electrons and protons. Very high energy. Those are diverted by the magnetic field around this region, and the Titan moon or Titan is actually swimming in it. So it gets irradiated by this high energy radiation very strongly, and it can produce such material by radiation processing. Okay? So these are the actual measurements which are done in space in Titan. So people have found large molecules being formed in Titan due to this high energy radiation. Okay? I'll skip this part. Okay? So we wanted to dig deeper and understand, is it possible, because normally high energy radiation is something we use to destroy things. Radiotherapy you have heard of? We use high energy radiation to actually damage biomolecules, not construct them. Right? So that sounds little far-fetched. Okay? And actually if you look at it, it is indeed true. Radiation actually should damage, not construct. But something else happens. Okay? What happens? So we start with this kind of simple molecules and we shoot them with different types of radiation. Because we know what sort of radiation they will experience there, we just replicate that in the lab. Okay? And then we try to understand what are the mechanisms by which they produce pieces. Because they break. They will break. What is interesting is what these broken pieces do. We discover a lot of interesting things what these broken pieces can do. These broken pieces, if they are allowed to come close to other broken pieces, they become very quick partners and forming larger molecules. So instead of causing permanent damage to the system, this radiation can actually provide a mechanism to collaborate, to join, to become bigger. Okay? So this is what we are exploring. We have been doing this work for like 10 years now. So there is a journal here, Astro PH. It's based in Leiden in Netherlands. Last year in October, the one full edition of this journal was given to us to highlight our work, what we did. You can, this is open. This is just a open journal. You can see this on the website. Okay. Now, how do we do this? This is one ion neutral coincidence mass spectrometer, what we have built at Iist. This is built by my PhD students. This is the electron impact system, electron impact mass spectrometer. What we do here, I'm not going to get into the technical details, but I'll just tell you what we do here. Here, we take these kind of molecules and shoot them with a, you see this white box here? It's a tunable laser. It can produce any wavelength between 230 nanometers to 2600 nanometers. That is very deep ultraviolet to infrared. Just on a press of button, I can get any laser out. And it's a pulse laser, nanosecond, so it is very powerful. So we shoot this onto these molecules and see how they behave. In this setup, we do the same, but with electrons, high energy electrons. This is a facility in New Delhi where we do this with the high energy protons. This is a facility which is under UGC, so we get a beam time there. Then when it comes to extreme UV radiation similar to what comes from sun, that no laser can produce. So we have a special facility in Italy where we go there to do this experiment very regularly. In fact, this October again we have an experiment scheduled there. This is in Trieste. It's a very famous place. ICTP is in Trieste. So this is how we make sure that we can cover all this: high energy protons, high energy photons, electrons, and so on. We try to identify how these molecules break. Okay, but so far I have shown you how these molecules break. I also told you under some conditions they can combine also. That I haven't shown you, so I'll show you now. If I want to do that, I need to hold them somewhere. So holding the ions is complicated because we are already doing experiment in the vacuum chamber. And ion or a molecule is a very, very tiny thing. You cannot just hold it. So we built something called an ion trap, radio frequency ion trap. So this is the ion trap device which is under construction right now at Iist. This is a bit old picture. My most recent PhD student, she is building this. This is the inside structure. Okay, this is where the ion trap is, and we produce the ions here, and then they are admitted into the vacuum, guided into the trap, and then we hold them there, and then we break them and see how they react. Okay, this is the actual picture. This is again fabricated there only. This is a RF ion trap, so we need to have RF radio frequency generator and amplifiers and so on. This is also built by my student Amrita, and meaning even the PCB she has made, and she is MSc Physics. Okay, so this drawing is also hers. In fact, she has much more complicated drawing. I have only taken the ion source part. So, and then this has to be you can't operate it manually. It needs to be completely automatic. So that is interfaced using a very cheap Arduino controller. She has just made a small program. The RF and the Arduino controller together operates this trap, and whenever the trap pulse comes, you can see the ions are coming out. We can hold the ions for several milliseconds or sometimes even a second. I'm not getting into the details, but this has a great significance. Once it's fully commissioned, it will be there are only 2 such ion traps in the country at present. Both are being under development. They are not fully developed yet. Both are being developed. So now, the last part, how this work and the first one is related. So the part which I did not tell you about Titan is all these reactions in Titan happen in Titan's ionosphere. The same ionosphere which our probe is studying on Earth. So the plasma actually assists in this process of producing chemical reactions and producing larger molecules. So while we are trying to find very fine reasons, so all these instruments help us to find case by case, how one molecule will react with another. But there are thousands of molecules, right? Finally, everything will happen as a khichdi, right? When you take a garam masala recipe, the combination of garam masala depends on which place and to whom you're talking. At a molecular level, something definitely is happening, but there are so many things happening, you cannot piece by piece analyze it. At the end of the day, you will cook it, taste it. If you feels good, very nice. Let's go ahead. Okay. So while we are trying to understand the microscopic reasons, we are also trying to understand as a whole how the system is behaving. So for that, we created another system, our factory of garam masala here. Okay. This we call as Titan reactor. What we did is we took 96% nitrogen, 4% methane. Put it inside this glass tube here. It's not glass actually, it is quartz. Okay. And you see this big box here and this big box? This box actually produces very high power radio frequency, 13.56 megahertz. And that is fed into an antenna here. Okay. And that produces this. This is a plasma. Okay. This is a nitrogen methane plasma. We put nitrogen and we put only methane. Okay. Methane is CH4, nitrogen is N2. Okay. And when we did this, we also put inside some small pieces of silicon crystal. Okay. And we also connected, so that silicon crystal we keep for some purpose. After the experiment, we took out that silicon crystal and then we studied something called FTIR spectrum, Fourier transform infrared spectrum. Okay. And that Fourier transform infrared spectrum is here. This is our sample. If you remember this picture, when the lander landed on Titan, it also did FTIR of this sample there around Saturn. Okay. And that data is here. They match. So we are able to produce the same material which is there in Titan by creating ionosphere like conditions on ground. Then the next question, can they host biomolecules, biologically important molecules? So what did we do? This is just some FM analysis and STM analysis and so on. I will not talk about that. So we wanted to also see if they can host some other molecules. So what did we do? We attached another tube here like this, quartz tube, dipped this quartz tube in liquid nitrogen, collected all the gaseous material it produced onto this tube, and then after stopping the plasma, we fed that thing into another chamber to do a mass spectrometry measurement. Okay. And with that we identified, remember, mass of nitrogen molecule is 28 and mass of methane molecule is 16. So you should have got a peak here at 16 and at 28. Look at the number of peaks we get. These are all molecules which are produced in that plasma. Okay. So this plasma which you see here, of course this plasma is a very high density plasma because in the lab we can only produce this. In space you have a lot of space. Okay. So there the plasma is very low density, but it has a very large volume. So it does the same thing. There is scaling. Okay. So because of that we are able to produce very interesting molecules. And by the way, I must mention that all this hard work was done by one girl. She was doing MTech in our solid state technology course, originally MSc physics, very hard working. She got very good offers, 3 places from foreign universities for PhD. And finally, she also got an offer as a scientist in a center in New Delhi. So now she has joined there. It's a permanent central government job. So she joined there. Very bright and very hard-working girl. And this all is built by her. Basically, whatever you see, you will find our kids really physically tightening bolts, cutting metal and things like that. They do all that. And it is all fun. Okay? We don't take it very seriously. We just enjoy. Okay? So, now keeping these things in mind, this is my second last slide. So keeping all this in mind, we conducted anyway a big conference in Iist this year. So as a part of that conference, we conducted a small session. Okay, it's called a brainstorming session on organics in space, because we believe that now in India this community is very small, very small. So we believe that now that Indian space program is expanding and we will be going to other planets, we will, in fact ISRO is preparing for a sample return mission where we will go somewhere, maybe moon, maybe another asteroid or another planet, we will bring a sample from there. Okay. So whenever you talk about a space program, you again ask the same 3 questions: why, what and how. Okay. Right. So if we sensitize people, then this is a fantastic why. Why should I go there? This is a fantastic reason to go there. Okay? And then with our research we can tell what exactly to do, to look for. And then the experts from ISRO can tell us how to do it. Right? How to go there, how to collect the sample, how to bring it. Right? So that is why we want to sensitize Indian academia, universities, research institutes. So we had more than 300 participants. They came to Iist. It was an occasion. They came for another conference on atomic and molecular physics, a big conference. So in that we conducted one session which was chaired by ISRO chairman, and we tried to sensitize the community that look, this is something very interesting and ISRO is expanding. If we now put a problem to ISRO that see there is organic material to study in space, then they might actually take up such missions on priority, right? Because now the government policy is very stringent. Government says if the people of the country, if the universities and research centers of the country need a space mission, then the Indian Space Agency has to provide it. Okay? So if we create good interest among the academia for such a topic, then it will help ISRO to make a decision. Okay? So that's why we want to conduct this program. So we invited a lot of people and it was a very successful program. And the next one is going to happen, focused program, not part of a conference but a conference itself on this topic. We are going to hold at Iist in next year in January. Our main focus will be to attract young faculty members from universities and colleges, and we will help them write proposals together with experts and start some research in their labs, build their own labs, so that we can encourage ISRO to participate, encourage universities to participate, encourage young people like you to participate and grow this. This requires a lot of research. Okay. Anyway, this is our more or less the dream. Of course, this kind of work cannot be done by one person, so we have a large collaboration. This is only a small part of it. There are a lot of people who have come and gone in the collaboration. These are different places where we have active collaboration. And this is the last slide, the actual answer to the question why. Okay. For an academic institution, it doesn't matter how many research papers are published, how many patents are granted. Actually, it doesn't matter. I know many people give value to it, but in my view, that is not important. Finally, what is important is what is the quality of the students which come out. Okay. This is a list. On the left hand side, this is the list of the white colors are the ones who are already working presently in our group in different aspects. These 4 are my PhD students. These 3 already have finished their PhDs with me. There are other 4, but they are ISRO sponsored. They don't work at Iist. Then these are project students, they are master students. Then I have some 4 project staff, and these are also master students doing research projects with me. These are all our former students who worked in these labs, 3 labs, whatever I showed you, and what they are doing at present. And of course, a large number of them, I have not listed here, those are working for ISRO. That's why I didn't specially write their names. So finally, what matters is what you actually produce. And that is strong enough why to get into any research and development activity in an academic institute. So ours is an academic institute, though we are part of Indian Department of Space. And having students around really helps us to do better. Really far better than what you can even imagine. So thank you very much.
If anyone has question, so can you ask?
Okay. So obviously the shortest answer is to study Sun and Venus, but there are many ways of studying them. So the advantage of Aditya L1 is that you will be watching this in a certain location. You know what is a L1? L1 stands for what, you know? It's called Lagrange point. So for a star and a planet system, there is a star and we are going around it. So for a star and a planet system, there are 5 points which are very special. These are called Lagrange points. So L1 point is a point which is right in between Earth and Sun. Okay. Not exactly centered, it's sort of mass centered. And from there, it will be constantly watching the Sun and sending us this information to Earth. Okay. So it will be basically able to, because we never actually see the anger of Sun directly, because we have such a nice protection on top of us, it never reaches us directly. Even if I put a satellite around it, no, you will not see the direct effect, because Earth's magnetic field starts affecting some 30,000–40,000 kilometers away from Earth. Okay. But at L1 point, we will be seeing the Sun's anger in its raw form, the actual energy involved in that. Okay. So that input will be useful for us. So if something happens in our atmosphere, if I can make a correlation between the two, I will be able to understand the interaction between the Sun and Earth better. So that is the purpose of, basically the purpose of Aditya L1. For Shukrayan, there are several things which we want to understand, because you know the problem with Venus is a very high density atmosphere, and that high density atmosphere has many structures inside. In fact, one theory is that there may be living organisms on Venus in the clouds. If you could jump on normally if you jump from an aeroplane or a spacecraft, you won't survive, right? But on Venus you will survive, because you will come down, and at somewhere some 30–40 kilometers from the surface you will actually float, because the ground pressure is 90 bar. Okay, you can't reach the ground. So it's a problem. Buoyancy will not let you come down. Okay, so it's possible that there are actually living organisms. That's a very crazy theory. That is not scientifically not very well proven, okay, don't quote me. But so the idea there is that we want to study the more scientific things. This is only story. The more scientific things which we would like to study is how the pattern of the clouds is, how the cloud movement is. Another very interesting, some of our colleagues are interested, is the lightning in Venus. You can ask why it matters. The reason was actually shown already, the plasma. The lightning actually produces that kind of plasma which can produce reactions. So we want to know whether lightning happens. So all this we want to study there. And there are many other things. Our sensor is also going to study the ionosphere and so on. What pieces of? Debris. Yes.
So as the number of the pieces increases, then the number of the collision rate also increases.
Yes.
So as collision increases, that means more debris.
Yes.
So, sir, as we want to send a particular satellite to our destination, so for that purpose means disaster rate is also increasing for that. So, sir, my question is that what is the ISRO plan to reduce these debris which are orbiting around the Earth?
Okay. So, yeah, so there are multiple ways of doing this. It's a problem. At present, all space agencies, not only ISRO, all space agencies, what they are doing now is there are international organizations. One of the major organization is called NORAD. It's a North American, basically it's an old missile defense system, but now it is, some of its data they make public, where they track all these debris. So they alert each other that your satellite is going to be crossing a path with this piece or that piece. And then momentarily they will move it. Like just the day before yesterday, they moved the International Space Station little bit down to avoid this collision. And then it went back to its orbit. So at present, people are mitigating this by doing this kind of temporary adjustments. Like ISRO, in one of the missions, ISRO delayed the launch by a few minutes just to avoid a possible crossover. So far looks like things are safe if we do this, but it's not going to be like this for long. So there are now experiments which are being done by a lot of startups, lot of companies and space agencies to, whatever junk is floating around, you either push it out or push it down. So very soon we will actually start cleaning the junk we have created, otherwise we cannot go anywhere. But yes, it's a problem, but it's not a problem just yet. Okay.
Sir, I also have a question. What are the difficulties and challenge that ISRO was faced in mission and Chandrayaan 3 mission?
I'll tell you, it's very, it might sound insensitive to ISRO, but because I have been working with, I am not from ISRO actually, I have some official position there, but actually I am a teacher. But I have been associated with them since 2012, and I am in several committees and this and that. So I get to see their work style and I work with them. I work in multiple ISRO centers also. So something very interesting I see about these people. First, they are very simple, ordinary people. If you see them in a supermarket or a shop, you can't say, this is some great scientist. No, they are very humble people. Second, for them, challenges is something which happens every day. If you see, I drive a car, okay? Suppose my car starts making a making a noise which is equivalent to, say, a flute. Okay? It's a very strange problem, right? So then somebody will say, "Arey, how can car make such kind of sound?" And then some research might happen. So it's an exceptional situation. Because cars, there are millions of cars running, everything is normal. Space technology is not like that. Every launch is a challenge. Every button they press is an exception. So they take it that seriously, they analyze it that seriously. So for them it is a lifestyle, and that is one of the things I really appreciate working with my ISRO colleagues, is that they never will tell you, "Oh, this is such a great challenge." If you ask them this question, they will be confused what to tell. Everything is a challenge. Okay? Everything is a challenge for them. Just because I did it yesterday doesn't mean today it is not a challenge. Every day is a challenge for them, and they triumph over their challenge. And that is what I enjoy the most when I sit in the committees, listen to them, how they solve the problem. Okay? That is one of the best learning experience you will have. But if I want to give some few points, for your curiosity, the few points, okay? When you send something to space, okay, if it is around the earth, it is close to you, it is very much in visibility, and if your antennas cannot see it, you can actually hire some other space agency's antenna, they will watch it for you, no problem. As you go away from the earth, the signal becomes weaker and weaker, and the distances are longer and longer, and the moon, when you launch, the moon is there. That doesn't mean you should shoot the rocket there, because when the rocket reaches there, moon will not be there. So one of the biggest challenge is the propagation of the position, कि आज moon कहाँ पे है और जब मैं पहुँचूंगा वहाँ पे तब वो कहाँ होगा. Okay? And these margins are very narrow. अगर आप थोड़ा इधर या उधर हो गए तो you will never get caught around the moon, or you will crash on the moon. Okay? So this is done, and in fact I think one of the best ability of ISRO is this, that Mars mission which ISRO accomplished. Okay? It was the most efficient trajectory to Mars by any spacecraft ever in the history. It will reach there very accurately, so accurately that it was designed to survive for 6 months, but it left with so much of fuel that it survived for more than 4 years. As simple as that. So that is, they use very special supercomputers to basically propagate this. So this is the first challenge. Communication, as you go further, signal is weak, that is second challenge. Third challenge is control. Once you have reached there, you have to do something. If you simply want to go into the orbit, it may not be that big a challenge. You may have to fire 1 or 2 thrusters, get into the orbit. But when to fire and which direction to fire, you cannot guide from here, because this is too far away. That has to be decided by the spacecraft by itself. So you have to program it like that. That is a challenge. For Chandrayaan mission, Chandrayaan 2 and Chandrayaan 3 was, see, firing a rocket is one operation. Any mechanical movement is a challenge in space. Now here you are talking about something separating from one spacecraft, right? That means they are going to push each other. You have to correct them. So this is a very big challenge. And then you have to land in some place. Okay? So where you are going to land, whether that place is safe enough to land, whether your orientation is right to land, whether your corrections are done properly, and you cannot control anything from ground. The computer on board has to say, yes, this position is correct, my orientation is correct, and if there is a mistake, it should know every possible scenario, what all can go wrong, and it should be able to correct it. Okay? So that is where a lot of thinking goes. Launching it into the space is the easiest part.
Thank you, sir, for clearing our doubt. Thank you so much for sharing your valuable time with us. Now I request Richa madam to voting thanks.
Thank you, one and all. It gave me an immense pleasure to offer an official vote of thanks for today's program. To start with, I'll thank our president, our management for providing us this space where we could conduct this lecture for enlightening our students who have got much motivated by just listening the name of ISRO. Volunteers who have taken a lot of efforts to make this program a grand success. Maybe those volunteers are controlling the students in different classrooms. Some students who are making the rangolis and many other things which they have worked on. Okay, so it gave me an immense pleasure to say thank you to all. Now, before ending this program, formally, I request Sangeeta madam to add few words to it.
Actually, I have got so many words, but then my students are waiting in G2, G3 and 210 very anxiously. But then I would like to just enlighten that sir has told us WWH. What, why, what and how. So how I put that? What a wonderful, highly inspiration session. I have just got inspiration from you, sir. Because for arranging this session, generally we arrange in the G3. But this time number of students were so more. We have tried to arrange over here and then make it live stream. And for that was a suggestion. We were trying to do it from last 1 week. But then I was in touch with Geetha madam, our principal madam. She's in USA at present. But then she said that go to Neura School and go stream from there. But then I said our conference room is the best in the Ulhasnagar. So we just tried, and I thank Bharat Khatri, our technical team head. He is a lot of support. We are sitting arranging from last 3 days. Since morning to evening we are here for arranging this, because arranging and streaming on the spot is not an easy job for us. But thanks to Bharat, he is very expert, and thanks to Ragir sir and Lala sir, Ganesh sir, Kuldeep sir and the technical team. But the main thanks I'm just saying because I always say from my heart. That's why I said this is the vote of thanks from heart. So I just want to thank Bharat a lot, and Geetha madam also, because she encouraged that we should go for a higher scale. And all the students who have taken pains, and really they were so excited. I want to thank Omkar. You were inspiration, because the way you said I want to come, I was so happy. And Ganesh sir, Bhagat sir, and my little angel Ashwin. Thank you, beta. Thank you for coming over here. Thanks to, I think UMESH sir, I was in touch. I was waiting eagerly that when I will be here in the Department of Physics as a HOD, I will just call UMESH. I just was searching, and I think the blessing of my God, that the moment I joined in January, I got the contact. That is a blessing, I can say, and the miracle. In January only I came to know Samuel, and from them I came to know about the UMESH contact number. So thanks to all who are standing behind the scene, on the scene, and thanks to my God. Thank you so much to all of you. Motwani sir has come to UMESH sir. Our Motwani sir from Hindi department head has come to felicitate you. Please, sir. Thank you, sir. Thank you so much. Thank you so much. I think we will be going to all the, we'll be going to all the classrooms. Please, student, please wait. You have waited for so long. Just sir is on the round only. Will coming in shortly. Okay? And now we are giving a feedback link. It is a QR code is given on the screen. Please scan and put the feedback. Thank you so much. Thank you so much to all the teachers also. So we are ending the session.